I'd like to introduce our first speaker, Martin Bridson from the University of Oxford. He's going to tell us about the geometry of the conjugacy problem. Take it away, Martin.
Thank you. It's a good pleasure to be back in Cambridge, see so many interesting people. So I'm going to talk about the geometry of the conjugacy problem. And most of what I say is going to be joint work with Tim Riley, some with Andrew Sale, and some with other people whose names will show up. I really put the insistence is on the geometry of the conjugacy problem. And I'm determined, so I do have a colloquium-style survey talk on this, but I'm determined not to give that today. I actually want to, given the audience, share some of the ideas that go into this and actually try and talk about some of the geometry to indicate what I've actually been up to. I might also say, in some sense, this isn't new, well, isn't all new, because during COVID I sort of got obsessed with this. But I know when I was sitting at home, but I didn't finish all of those papers at the time. So if you look on the archive, you'll see I've just put 5 papers up on this subject, and there's another 3 or 4 before Christmas. That's partly because I went on sabbatical for 3 months, which was fantastic. But it's partly because these things were largely done a while ago, and they're just being updated. But what's the point? So, let me start with the geometric version. So the word problem, as you know, can be thought of geometrically about how hard it is to fill loops in non-homotopic loops in manifolds. So what's the conjugacy problem? As you also all know, the conjugacy problem is about free homotopy. Okay, so conjugacy classes in pi1 of a space, say a manifold, of course correspond to free homotopy classes of loops. And I'm interested in the sort of complexity of the conjugacy problem, or to measure how hard the conjugacy problem is. And so that's really about the geometry of annuli mapped into this, let's say a manifold. And so you're really studying the geometry of annuli in a manifold. So I'm interested, and you got 2 loops of a given length, and then you're interested in efficient annuli, so that this goes on this end and this goes on that end. Not embedded, of course, just mapped in, okay, just immersed. And then how hard the conjugacy problem should be to do with the geometry of these annuli. And so a basic thing you might talk about is the homotopy width for maps of S1 into your manifold. And put an n there, that's for length, n, because I'm going to discretize everything. And so what would this be? This would be sort of, you would look at, I'm not going to write all this out in great detail, but let's say the length of the annulus, okay, and it's going to connect my 2 loops, U and V. So these are my 2 loops, U and V. I might minimize the length of the annulus over all the annuli with those ends, right? And then I'll take the supremum over all loops where the lengths of the loops are supposed to end. Okay? So I'd just be looking at how long does this annulus have to be to connect that guy to that guy. Okay? And length, of course, would just, well, in any reasonable sense. So you could pull back the Riemannian metric if this is smooth embedding and just measure how far it is from this end to that end in the annulus. Okay? Now that's not the only thing you can do. Okay? You might instead of looking at the length of the annulus, discuss the area of the annulus. Right? So if you instead discuss the area of annuli, that will give you something which we call the annular Dane function, which I'm not going to talk about today, but which you can also study and has interesting properties. But that's basically what I'm interested in, okay? The geometry of annuli in manifolds. Now, what does that correspond to algebraically? So we all know that conjugacy corresponds to free homotopy, and so conjugators correspond to annuli. And so the algebraic version of that, and I'm trying, I always sort of feel that the morally correct thing to do is work with finite presented groups, right? Now, you could just do all of this stuff I'm about to do with finite generated groups, but I really think you should do finite presented groups. Well, I'm going to do finite presented groups. So the conjugator length of two elements is the, you want to minimize, I hope I got my mins and maxes right over there, the length of words W, so that W inverse U W equals V. Okay, so that's if two words are conjugate in gamma. Now, I'm saying words, but it's really just elements, okay? So it really doesn't matter. Unlike the word problem, words versus elements doesn't really matter. I'll draw a picture in a minute to say why. Okay, so you can either think I'm talking about conjugacy between elements, or I'm thinking about conjugacy in the group between words and the generators. And then the conjugator length function of my group gamma, which depends on the presentation, but as ever in geometric group theory, it only depends on it after some sort of course by Lipschitz equivalence. So the conjugator length function at n will be what I'll do. So I'll look at the hardest problem up to length n and take the minimal conjugator okay, that's the minimum over W, and that's the max over U and V. Does that make sense? So you look at all pairs of words up to length n. Oh, sorry, better say something about n. So the distance from 1 to U, the distance from 1 to V, both less than equal to n. Or if you like, they're words of length less than equal to n. Okay, so it's take words of length up to n, describe elements of your group, look at pairs that conjugate and ask how long is the minimal conjugator. Now that should be, so the idea is that's a measure of the complexity of a direct attack. On the conjugacy problem. And for example, the proposition you can just convince yourself it's really just a tautology. So if gamma has a solvable word problem, so as long as there's an algorithm to recognize which words represent the identity, then the conjugator length function of gamma is recursive, bounded above by a recursive function equivalently, if and only if gamma has a solvable conjugacy problem. Now, I tried to choose my words carefully. It's the measure of complexity of a direct attack on the conjugacy problem in gamma. That's not to say there isn't some other way of solving the conjugacy problem, right? So often, if you look in the literature, people like Ashop would solve, you've got all sorts of nice work about solving the conjugacy problem by proving that groups are conjugacy separable, right? If you know that any two non-conjugate elements in your group remain non-conjugate in some finite quotient, then that solves the conjugacy problem, because you just enumerate all finite quotients and look to see if things are conjugate in there, and simultaneously you just look dumbly for conjugates. And that's kind of the analog of the fact that if a finely presented group is residually finite, then has a solvable word problem. Okay? Now that doesn't give you a bound on complexity, it just gives you a solution. And the idea here is we want to bound conjugacy length functions to get a bound on how complex conjugacy problems are. I might say there's lots of situations where conjugacy problems are shown to be solvable by having a list of invariants and then proving that they're a complete list of invariants. Now, two things are conjugate if and only if this list of invariants is the same. And that doesn't immediately give bounds on the conjugacy length function, though I think it's an interesting problem in those sort of situations to figure out what the conjugator length function is once you know it is recursive. And in fact, an example, so SLNZ. So a long time ago, Fritz Grunewald gave me a hard time over me saying conjugacy problem was easy in SLNZ, and it's not. That's just false. It's easy to decide if two matrices in SLNC are conjugate, but in SLNZ it's a subtle problem involving arithmetic. Okay? And it is solvable, but that proof doesn't seem to obviously give you a bound on conjugated length. I think that's an interesting problem. So this is what I'm interested in. Okay, I've got a bit obsessed about conjugated length functions, the geometry of annuli. We could also talk about annular Dane functions, which correspond to the area of these annuli, but I'm not going to talk about that today. Okay, and so the sort of combinatorial geometry, which will be hidden in the background today, is annular Van Kampen diagrams. Okay, so just as the bridge between the study of Dane functions for groups and isoparametric functions for manifolds, the context of the word problem is regular disk Van Kampen diagrams. So the combinatorial geometry that bridges between the algebra and sort of the manifold geometry here are annular Van Kampen diagrams. So that would be Van Kampen diagrams, that is planar two complexes tiled with two cells labeled by the relations that exhibit the conjugacy from one element to the other. Okay? And what we're talking about with the conjugated length is, so this is a Van Kampen diagram, but that is to say it's a planar two complex with tiled so that each two cell is labeled by a relator of the group, and that the inner boundary label is labeled by one word u, the outer by v. They have base points, and what you're looking for is to try and minimize the length of this path from here to here. Okay, I've said that very quickly, so if you're familiar with Van Kampen diagrams, this should make sense. If you're not, don't worry about it. I'm not going to use them in the rest of the talk. But I do want to, I should have drawn that picture bigger. Let me just...
Are they always homeomorphic to an annulus?
They're not homeomorphic to an annulus, no. They're planar and they can be singular, so that they're homotopy equivalent to a circle. So they can be singular. Yeah, so yeah, it's perfectly allowed to have some diagram like that. That's fine. Or even some branching up here, right? For you, so you're out of circle, and then do that. And you're in a circle, we'll do that. Yeah, no, it's perfectly allowed for them to be singular. And in fact, that singularity is important. But let me just draw one picture to justify what I was, to try and justify what I was saying about not really matching whether you do elements or words in these functions. So if you're dealing with words, I had u on the inside and v on the outside. Try to make sure they go the right way. Suppose you've got, so when you're dealing with diagrams, it's really about words, right? Your words have to label the circuits on the inner and outer labels of this diagram. But you see, if you give me some other word representing the same group element, then, let's say u. So you give me some other word representing the same group element, well then there'll be some Van Kampen diagram, a disk diagram showing that u equals u prime in the group. Okay. But I could take that diagram, delta, and I could stick those ends together, and then I could just stick that diagram in there. Right, so that would be delta, that would be u prime. Okay, and I get, so I've got that, I just take this, I stick those two ends together, and then I stick the delta there. Now I've got a new annular Van Kampen diagram, where the inside label isn't u anymore, it's u prime, this other word representing the same group element, but I didn't change the conjugated length, because the conjugated length is just the length of the shortest path from here to here. Okay. So it doesn't matter whether I talk about words or group elements when I'm doing this conjugated length function. Okay, it's kind of swept up in the definition. Okay, so there's two obvious questions. Question one: which functions are conjugated length functions of finite percentage groups? Now everything is, on the first speaker, I might as well write it down, up to coarse equivalence. Now actually you can be a bit, usually it's actually just by Lipschitz equivalence, but let's say that coarse equivalence here. So F is sort of the same as G, if F is sort of less than G and G is sort of less than F, where that means F being sort of less than G, I'm sure you all know this, there exists some constant so that for all n, just stick a constant everywhere you feel like it. F is less than or equal to constant times G of constant times n plus constant plus constant. You probably don't need that many constants, but there's no harm in it. Okay, they're just coarsely the same. So all quadratics are the same, all cubics are the same. Cubics are different to quadratics. Single exponentials are different to double exponentials, etc. So whenever I say which functions are conjugated length functions of finite percent of groups, you could take that to be a precise question and ask about the coefficients in a polynomial with a specific presentation or something. But I really care about groups and not presentations. And if you change presentation, this function will change in that sense, right? It'll give you an equivalent function. So it's always up to coarse equivalence. And then the second question, second obvious meta question, is what is the conjugated length function for, well, if one was being pompous, one might say natural families of groups. I guess that's the intellectually polite thing to say, but what we really usually mean by that is for our favorite groups. Now, lots of people have worked on conjugacy problems, of course, so there are lots of partial answers to this in the literature, but there's also an awful lot that isn't known. And even in cases where the conjugacy problem is solved, as I was trying to indicate by talking about SLNZ, we don't necessarily know the answer to this question. Okay, so after we've solved the conjugacy problem for order out of Fn, for example, we can then ask what its conjugated length function is. That'll keep us busy. Okay. So that's the context, and I want to talk about some answers to these questions, but I really today want to focus on this question. That's what I'm thinking about. Now, which functions are conjugated length functions of finite percent of groups? Now, there's different sort of answers you might have to this, just as in the 90s and the 2000s when people were busy working on Dane functions. There's an eraser somewhere. Huh. That's interesting. Oh, yeah, thanks. You might sort of say, well, there might be an answer like, well, they're all reasonable time functions of Turing machines. That might well be true, okay? Yes, think about what reasonable means. Or you might try and construct nice geometries that give you specific behaviors. And I'm going to talk about the latter, okay? Trying to think about nice geometries that will exhibit a wide range of behavior for conjugacy length functions. But before I sort of start listing things like that, let's have a thought. Might conjugacy length functions, that is the class of conjugacy length functions, be the same as Dane functions? Quite possibly. Okay? They might be all reasonably computable functions. Just to remind you, Dane function of finite percentage group is the sort of analog where you take a direct geometric measure of the complexity of the word problem. So if you've got a word in the free group on the A's, and word equals the identity in gamma, well, what's that mean? It means that there's a free equality like that, with rho I, one of the defining relations, words. And how hard it is to prove that word represents the identity in the group. If you attack it naively, depends on how many relations you have to use. That's sort of the length of the proof that the word represents the identity. So you define the area of W to be the least A in all such expressions. And then the Dane function of the group, again, dependent on the presentation, but only of course equivalence, is the maximum of the area of words. W is a word of length that belongs to N that represents the identity of the group. Okay. So you might think that you Dane functions and conjugator length functions, one's for the conjugacy problem, one's for the word problem. We pretty much know, as a result of a lot of efforts, and the final theorem being due to Viger, Rips, and Sapir, that Dane functions of finely presented groups are roughly the time functions of Turing machines. Not quite. There's some qualification, but something like that. And you might think there's some way of translating Dane functions into conjugator length functions. That's a very reasonable thing to think, and there probably is a proof like that. But let me tell you what's a sort of negative theorem about. Let me tell you a negative theorem. And this is to do with fiber products. Now, it's well known, been known since the 70s, that fiber products sort of turn word problems into conjugacy problems. Now, what do I mean by that? So remember, if I've got two groups, gamma 1 and gamma 2, I've got gamma 1 and gamma 2 mapping onto some group Q, then the fiber product is the subgroup of gamma 1 plus gamma 2 consisting of pairs that have the same image in Q. Now they're a great source of building interesting groups, where you sort of translate pathologies or special properties of this quotient into properties of this group, but this group is a subgroup of this, and this might be a nice group. So it's a way of building complicated subgroups of nice groups. And a classic example of this, due to Mihailova, and then refined by Miller in the 70s, is that if Q, so let's say if Q is a finitely presented group with an unsolvable word problem, and you take the map of a free group onto Q and take that to be so this you take the fiber product of that map with itself, and the fiber product P in X cross F is 1, finite generated, that's easy, and 2 has an unsolvable conjugacy problem. Okay, so that taking a fiber product turns a hard word problem into a hard conjugacy problem. And in the context of looking at conjugator length functions, you might wonder, will I be able to get all sorts of conjugator length functions by doing fiber product constructions and knowing the complexity of the word problem in this quotient Q? Okay.
Could you please lift the board?
Oh, yes. Okay, so let me give you a couple of theorems, which are in a couple of these papers I wrote earlier this year about that. Now, I did think about giving a lecture just about this because it's got a surprising amount of nice hyperbolic geometry in it, in the sort of classic delta hyperbolic sense of drawing lots of triangles and chasing around diagrams. So these theorems sound purely algebraic, but in fact, they've got lots of nice combinatorial hyperbolic geometry in them. First theorem is so let H1 and H2 be torsion-free hyperbolic groups. P and H1 cross H2 subdirect product, full subdirect product. So subdirect product, remember, just means it's a subgroup that maps onto each of the factors. Okay. Now, there's a little lemma that's been rediscovered by lots of people, I think, independently, is that subdirect products of two factors are the same as fiber products. Okay, so i.e., just believe me, this is a standard fact, P is the fiber product of a pair of maps onto some standard, onto a group. Okay, how do you manufacture this group? So you manufacture that group. Q is just, you take one of the factors and you factor out the intersection of the five. Okay. It's just a little exercise to see. It doesn't matter whether you take H1 or H2 in that case, and you get these quotient maps. So let H1 and H2 be torsion-free hyperbolic groups. Take a subdirect product. Now, this is a one-sided theorem over here, right? It says that if the word problem in Q is bad, then the conjugacy problem in P is bad. I want an if and only if statement. Okay, so then I want to say the conjugacy problem in in P is solvable if and only if, well, first of all, I'm going to have to put here the word problem in Q is solvable. Now, I'd like to stop there, right? Because then I'd really say that fiber products are translating word problems into conjugacy problems. But unfortunately, I can't stop there. You need another condition. And what's called the power problem. Well, it's called the power problem in the older literature. In Q is solvable. I.e., there exists an algorithm that, given two words in the generators, U and V, think of themselves as a Q, decides if U is in the subgroup generated by V. So there's a uniform solution to the membership problem for cyclic subgroups in this quotient Q. Now this is a more subtle condition than it looks. And this caused me a lot of pain. Solving the power problem does not solve the order problem. So you necessarily have to decide if a word U belongs to is a power of V without deciding whether U and V are elements of finite order or not. There are groups where you can't decide which elements have finite order or not, but you can nevertheless decide membership of cyclic subgroups. Okay? So this is a subtle problem that sort of points at the fact that, what this is really about is the geometry of cyclic subgroups in Q. Okay? This is saying that there's a uniform bound on the distortion of cyclic subgroups in the quotient Q. And it doesn't matter, and you have to include both finite and infinite cyclic subgroups and not distinguish between them. Okay. So does the theorem make sense? No. Yeah?
So, but the power problem does imply the word problem, doesn't it? So you could...
The power problem does include yeah. So yeah, Henry's quite right. If you take the trivial group as your cyclic subgroup, then it's the word problem as well. I just separated it out in order to make the following remark. What matters for us is the word problem alone is not enough. Word problem alone is not enough. Okay, so, and this is in the context of, remember, sort of the way I've set up today's talk, I'm trying to talk about conjugacy problems and want to think about the possible complexities of conjugacy functions, conjugacy length functions, how complex conjugacy problems can be, I'd like to say, well, you can just translate word problems into conjugacy problems, and since we know everything there is to know about the complexity of word problems, we'll know everything there is to know about conjugacy problems. This says that isn't true, okay, at least with this mechanism, okay? So I can't just go around writing down fiber products and say I don't have to bother calculating conjugacy length functions because I can just get any conjugacy length function I want by using a Dane function. There is nevertheless a positive theorem here. Well, there's a whole bunch of positive theorems, but I'm just going to state one because it's the least technical one. That is, for all standard Dane functions, delta n, so anything that arises as the Dane function of a finite presented group, except I've stuck in the word standard here. I'll just say it without writing it down. Standard means you're the Dane function, not just of a finite presented group, but of a group with of type F3, with a finite 3, with a classifying space has a finite 3 skeleton. Every known Dane function is also the Dane function of a group of type F3, but it's not clear if that's true in general. Let me not say it. For all, there exists a finitely presented group, which I'll call P because it's constructed as a fiber product, but I'm not going to tell you how, such that. So what we're interested in is calculating conjugator length functions, okay? I would like to say that if you give me a Dane function, I can make a group that has the same conjugator length function. Can't say that, well, that's probably true, but it can say, so there are more technical theorems, but this is the easiest one to state. You can bound it below by just some n times the conjugator, the Dane function. You can bound it above by something a bit bigger. I just have to put some squares in. So at least, you know, you can squeeze it between the conjugacy problem of the fiber product is bounded between Dane functions like this. Okay. Does that make sense? The quantifier is okay. So you give me a Dane function, means there is some finite presented group of that Dane function. I'll concoct another finite presented group using fiber products and some other stuff. So this conjugator length function can squeeze like this. Okay, right. So that's all I'm going to say about that. Except to say, you know, if you want to make, you know, if you get kicks out of making big functions, you know, you can make Dane functions that are bigger than that lie in any level of the Gregorchuk hierarchy of recursive functions. This will tell you can make conjugator length functions in any step of the Gregorchuk hierarchy. If you want something that's doubly exponential, this will let you make something that's doubly exponential in a very explicit way, and so on. Okay, but
your group P does it have type F3?
Sorry?
The group P you construct, does it also have type F3?
Yeah, it does, yeah. Oh, actually. That isn't in the paper. No, but I think you could do it. Yeah, 3, I think. Yeah, but that's not written down. It's,
because it would be natural. Right?
Yeah, no, it would be natural. Yeah. No, that's not written down actually. Because the 1, 2, 3 theorem is used to prove it's finite presented. So you need to be in a situation where the 2, 3, 4 theorem works. But, okay, how am I doing for time? Okay, so I feel this lecture's been a bit dry so far. I haven't really shown you any geometry. But the remark is here that you're getting bounds, not exact calculations. In what's above. And that's kind of typical, right? That typically, if you look at the literature of what has been proved about conjugator length functions, you typically get upper bounds, because that's what people, you know, if you want to solve a conjugacy problem, you do it by saying, well, I know the solution to the word problem, and I know that I know if two things are conjugate, then they're conjugate by an element whose length is at most quadratic in the given words. So now I've solved the conjugacy problem. Okay? That's a sort of a rational thing to have done to solve the conjugacy problem. And so typically, if you look in the literature, you get lower bounds on conjugator length functions. If you look at solutions to conjugacy problems, getting sharp, matching lower bounds is harder. So I'm really not interested so much in theorems like this where you get bounds. I want to try and get exact calculations of conjugator length functions and ask which ones exist. Now, to motivate this, is this a bad place to write because of the lectern? Let me write over there. To motivate this, let me not crop. Let me compare to the way we came to understand, and I'm going to focus now on relatively small conjugator length functions, so things in the polynomial range. So let's compare the spectrum of conjugator length exponents, so the set of real numbers alpha, so that n to the alpha is up to equivalence the conjugator length function of some finite percentage group. Okay. Which numbers arise as the conjugator length, as the exponents of the conjugator length functions of some finite percentage group? Now that's a countable set of numbers, right? Because there's only countably many finite percentage group. What is that countable set of numbers? Well, the isoperimetric spectrum is something you could compare it to. The set of numbers that are Dane functions of some finite percentage group. And that, through a lot of work in the 90s and the first decade of this century, was understood, right? So the isoperimetric spectrum, at least its closure is 1. You get a dense set of exponents starting at 2, and what you get is of all reasonably calculable numbers. Now, I just want to talk a little bit about the history of how this came to be, and then to motivate questions and theorems about conjugator length functions. So what's the first thing we all learn in graduate school these days about the isoperimetric spectrum? First thing we know is that hyperbolic groups are characterized by the fact that so Dane functions being linear, that means the gamma, if and only if gamma is a hyperbolic group. Here, lots of things, lots of groups. Okay? So certainly hyperbolic groups, but lots of other things too. Right? Things like Thompson type groups have linear, some Thompson type groups have linear conjugator length functions. Mapping class groups have linear conjugator length functions. Lots of three-manifold groups, but not all of them, as we'll see in a minute. So there's lots of things. Right? There's no sort of analog to getting hyperbolicity or, as far as I can see, any reasonable geometry, uniform geometry out of having a linear conjugator length function. Okay. Then there's the fact that the isoperimetric spectrum has nothing between 1 and 2. Now, I see no reason why that should be true here, but I haven't been able to construct an example. Okay? So there's a challenge. Construct a group whose conjugator length function is faster than linear, but slower than quadratic. Yeah, I see no reason why that shouldn't exist, but I don't know how to make one. What was sort of then proved by Gromov and Baumsack, Miller and Short, myself and Christophe Pité, if you give me any integer, then you can construct a group whose Dane function is polynomial of any given integer degree. And so one of the first classes of examples are the model filiform groups. You take z to the d, acted on by z, so it's a d-dimensional torus bundle over the circle, where the holonomy is the sort of simplest unipotent matrix, ones in the diagonal and superdiagonal, call it gamma D. So the Dane function of that group, of gamma D, is polynomial of degree D plus 1. I shouldn't have done that. And right over here, let's go to theorem number 3, which I'm going to try and explain some of the geometry of to you. Those groups are going to be used again. So they're very nice models of nilpotent groups. They have graded Lie algebras. They have a nice Carnot geometry to them. And exploit that Carnot geometry. They're also come in a nice family where you can do an inductive proof on that integer D. And so the third theorem, paper of Riley, is that indeed you can get any integer exponent as a conjugated length function, and more precisely, the conjugated length function of the model filiform group is polynomial, not of degree D plus 1 like it was there, but of degree D. So that's the same model filiform group. Okay. I'm going to try and explain some of the geometry of that too. So you can get any integer exponent. Okay, so let's do 3 there. Now, what about arbitrary nilpotent groups? So there's a theorem here that if n is nilpotent of class C, remember that just means you keep taking commutation until it stops at class, you could have C steps, class C. Then the Dane function, there's a uniform bound in terms of the class, it's class plus 1. So a Beating group's quadratic, something like that, three-dimensional Heisenberg group is cubic and so on. There's a uniform bound. Does that work here? Okay. Well, it's quite a soft thing, as often is with nilpotent groups, to do some sort of induction on nilpotency class and number of generators and so on, to show that you can get a polynomial upper bound on the conjugated length function of any nilpotent group. The question is whether you can make it uniform in the class. Okay. So let me give you a theorem about that, and the answer is no. Which I think is interesting and leaves a lot of open questions. Again, this is in a different paper with Riley. So, say if gamma is nilpotent with class 2, now I actually have to say what it looks like here. So it's got some center, so it's a central extension. I should say that's central, it might not be the whole center. And this is abelian. Okay, that's what a two-step nilpotent group looks like, central extension with an abelian group. Now, if I was doing Dane functions, I would now just say it's Dane functions at most cubic. But here it's going to matter what this is here. And suppose this is virtually, so it's got some torsion-free rank, suppose it's virtually torsion-free of rank n. Okay, then the conjugated length function depends not only on the class, but it depends on that integer m there. I'm going to look at my notes to get it right. I don't want to be off by 1 here. And it's m plus 1. Oh, sorry, it's exactly n to the m plus 1. So you can say exactly, oh, sorry, no, that's not what I mean. It's in most sense, the m plus 1. That m is that m, yeah. Is that the question? Have I got more m's? It doesn't depend on the rank of A. It doesn't depend on the rank of A.
What if A is trivial?
That's okay. This is less than or equal to. Okay, but so it depends. Or look, the bound depends on this, on the rank of this. But well, what if that's true? That's perfectly fine. That's a bound. It's only a bound, and I was whinging before about people only proving bounds, right? Is it sharp? Well, there's a second part to this theorem, is that this is sharp, by which I mean there's an example, or a class of examples, many classes of examples. Let me give you one. I want to be as explicit as possible here. So let G sub m be, okay, it's got three sorts of generators. There's going to be m of those, it's going to be the same m. So down here, this is going to have rank m plus 2. Right? So that stuff is all going to lie in what was called A in that short exact sequence. And then you have the central generators, C1 up to Cn. Okay, so the Ci is central. So the AI commute with BJ, the AI and the AI commute with the commute. They don't do anything. B1 and B2 commute. Okay, but there's something had better happen between the A's and the B's to make this a non-trivial central extension, which I'm going to write down here in a second. But first, let me tell you what the conclusion is. Then, okay, so this has got a center of rank m. So there's an upper bound of rank of degree m plus 1. And here, the point is that this, in this family, that is sharp. It really is degree m plus 1. Okay, so it really does depend on the rank of the kernel, of the center, and not just the nilpotency class, for reasons I'll explain in a second. But I better tell you what these relations are. What is this group? So what relations have I not told you? I've not told you how the A's interact with the B's. There's only two B's, B1 and B2. So each, for I equal 1 up to m, AI will conjugate B1 to, I have to remember about my minus signs. That's why I'm holding my notes. No minus sign, CI. Okay, so it just pops out as CI. And for I equals 1 up to m minus 1, what AI will do to B2 is it will pop out a CI inverse, except it's not CI, it's CI plus 1. So I have to stop at m minus 1, and then a m will commute with B2. Okay. So there's an explicit nilpotent group. Now, why have I cooked up these relations? There is some geometry to it, but there's more arithmetic. So, let me.
Quick question, Have you done the explicit calculations for the Heisman groups?
Yes. Oh, not all of them. Sorry. Have I done? I don't think I've done it for all. But for the three-dimensional one, it's cubed. It's quadratic. But that was, I think that, yeah, it's quadratic for the three-dimensional. That's included in this family, oddly. Actually, yeah, that's there. Now, I'm not going to explain the geometry of this one to you, because I want to explain a bit about the geometry of this filiform result, and then I wanted to talk about fractional exponents. But I do want to sort of give you some hint as to why that second part of this theorem is true. Well, first of all, this is a very general thing. You should expect the proof to be quite general. It is. This has some special features that are, I think, worth exploring in other cases. And let me tell you words that are hard to conjugate in that group. So let U be B1, B2 to the n, A1 to the minus n, B1 to the minus n, A1 to the n, B1 to the n. Now I've written it out like that. So you can see 1, 2, 3, 4, 5. That's got length 5n plus 1. So it's linear in n. Okay, but a more concise way of writing that, if you pinch it into normal form, is B1, B2 to the n, C1 to the minus n squared. Okay. Take V to be just the first bit there, B1, B2 to the n. Right, so U and V differ by this central element. And that's going to keep coming up, these central discrepancies. I claim the unique shortest word conjugating U to V is W naught, which is A1n squared, A2n cubed, up to AM, which was the size of the rank of the center, to the n plus 1. That's the shortest word conjugating U to V. Now, the way that's done is by analyzing, so the title of the paper in which this is has something about systems of linear Diophantine equations. That sounds fancier than it is. That just means a bunch of linear equations with integer coefficients where you're looking for integer solutions. Okay? The idea is those things are conjugate. So you think of a typical conjugating element. It'll be a word in A's, B's, and C's. You give the exponents of C's names, x1 up to xm. That'll give you, trying to figure out when it conjugates will give you a system of linear Diophantine equations. And what you're interested in is the size of the smallest solution to that system of linear Diophantine equations. And there's a whole literature on getting small solutions to systems of linear Diophantine equations. And that's where that's where both this upper bound and the corresponding lower bound here come from. Okay. So that's, I think there's more to be explored in the geometry of the conjugacy problem, even for these two-step nilpotent groups. I say you can turn it into algebra and do these systems of linear Diophantine equations, but the geometry that goes with that's kind of interesting because it's definitely not coarse geometry. Okay? Now, I should have made this remark earlier. There is geometry here, thank God, but it's not generally, it's not all coarse geometry, and it can't be for the following reason. So, there exist finite presented groups, like G with index 2 and H with subgroup index 2 and G, so that G has a solvable conjugacy problem, but the subgroup of index 2, H, does not. That's Collins and Miller. So when you're trying to calculate conjugator length functions, or any sort of geometric invariance of the conjugacy problem, you have to be careful that you can't expect to proceed by arguments that work with quasi-isometry. Okay? Because here are two quasi-isometric groups in the strictest sense, right? Because one's got index 2 and the other, so that you lose the geometry of the conjugacy problem completely when you go from the big group to the little group. And you can do it the other way around as well. So whatever geometry you're going to use, it can't just be coarse geometry. It's got to, by necessity, have something, for example, arithmetic in it that requires you to be more precise in what you're doing. Well, I think I'm going to, since I'm running out of time, I think before I come back and discuss, so I want to come back and discuss, what did I do with, I want to come back and discuss this about the what geometry of the filiform groups goes into producing polynomial examples of any type. But first, I want to talk about the snowflake groups. Are there any questions while I'm... So back to, how did we come to know that the closure of the isoparametric spectrum was what I said it was? That was the snowflake groups that Noel Brady and I cooked up back in the 1990s. Okay, I love these things. You take yourself a torus, it's a free abelian group generated by A and B, and then you do a very simple thing. You stick on a tube, stable letter S, you stick on a second tube, stable letter T, and what do these tubes do? Well, one end is attached, of each is attached to a loop that wraps Q times around the A direction. I take an integer P bigger than Q, and what the other ends do, one of them wraps around A to the P times B, and one of them wraps around A to the P times B inverse. So the fundamental group of this little two complex I've just described, BPQ. So I've got A and B commute, and then S conjugates A to the Q to A to the PB, and T conjugates A to the Q to A to the PB inverse. What's interesting about those groups is, despite their harmless little description, the Dane function of this group is degree 2 to the alpha, where alpha is log to the base 2 of 2p over q. Okay, so that gives you transcendental exponents in the isoperimetric spectrum. It also gives you a dense set of exponents between 2 and infinity. Okay. So there's a reasonable place to look if we're trying to cook up conjugated length functions that might have non-integer exponents. Okay, so that's what I want to do. I want to sort of use the geometry of the snowflake groups. Let me explain to you why they're called, what's this business about snowflakes. I'm going to need this anyway. In a second, here's a proposition that if I just think about, this is to do with the distortion of the free abelian subgroup AB inside the snowflake group. What is it? Well, you can say very precisely what it is. There exists a constant so that for all x in the torus there, if you look at the distance in the torus between 1 and x, and you have to take that to the 1 over alpha, where alpha is that exponent over there, log to base 2, 2p over q. That is a lower bound on the distance in the ambient group, and it's also an upper bound. So a lot of distortions, when you do distortion calculations, it's not this precise, right? There's some additive stuff. You really need this tight bound, what I'm going to say. Okay, it really has to be Lipschitz on the nose. You can't allow an extra linear bit here or additive error. I really want that distortion very precisely. Now, why might you believe that is true? Well, this is where the snowflake geometry comes in. Well, think about the cyclic subgroup generated by A. Okay, let me try and convince you that that has weird distortion. So let's take some big power of A. Okay, but I'm going to sort of write that as 2p times something plus a little error. Okay, so think of that as a small error. Right, so you divide it by 2p as much as you can, then you got a small error. All right, so here's a path. Here's like a group element A to the n. N is big. Okay, lying in the torus. Now you've got this little error on the end, and then I can factor that as a to the n1, sorry, a to the p times b to the n1 times a to the p b inverse times n1. Everyone believe that? right? Because the B's cancel, right? This isn't an abelian group, A and B, and so you're just left with the A's. Okay, well that wasn't, well, so what? Okay, the point now is that's something that I can apply the stable letter T to. On the other side, what will pop out is HQ to the N1. And what will pop out if I put an S strip on this side is A to the Q N1. But P is bigger than Q. Okay, so what I've done here is I've taken something and I've essentially divided it by P and then multiplied it by Q. So the length of these strips is obtained from this essentially by multiplying by Q over P, which is less than 1. And then there'll be some slight error, and I'll be able to do the same thing again. And I'll be able to shrink it again. And then there'll be some slight error, and I'll do it again. And I'll keep going, shrinking exponentially as I go. Okay, so you'll be able to shrink length exponentially as you go out in this picture. And so after logarithmically many steps, you'll hit a constant value. And the area will be some sum that you'll have to calculate. But that's the basic geometry showing why this subgroup, the torus subgroup, is distorted in this weird way. And it also gives you an idea of why the Dane function might be weird, because it turns out that these are minimal area diagrams I'm sketching here. Right? So that's the geometry of the snowflake group. It's all to do with careful calculations of the distortion of this torus subgroup. So I want to use that in trying to cook up some interesting conjugator length functions. So I'm going to write a theorem here, and it's not going to be the theorem you think it is. If you're still awake, you think I'm about to write a theorem that says that the conjugator length function of BPQ is something weird. It's not, it's linear, sadly. It's another example of the fact that lots of interesting groups turn out to have conjugator length functions. So I'm going to modify this group. Okay, so I'm going to take BPQ plus to be, well, I'm going to have the generates and relations of B and Q, and I'm going to add another stable letter, and all that's going to do is commute with my generator B. Having done that, you think I've got something better. But now you think Bridson's really wasting my time because it's still linear. But I then take a central extension of this group where I keep the generators and relations of BPQ, but I now introduce a central letter Z, so it's just a Z central extension BPQ plus. And I replace this relation by theta conjugates B to BZ. And thank God we've finally got something interesting. The conjugator length function of that group is n to the alpha plus 1. Okay. So that gives us a dense set of exponents of conjugator length functions. That conjugator length spectrum is dense between 2 and infinity. Okay? It's probably dense between 1 and 2 as well, I would guess, but I don't know how to do it. Now, I've sadly not left myself enough time to explain the geometry of the filiform groups or why central extensions come in. But I've sort of said central extensions or central letters a lot, right? And there's some very nice geometry that goes with what happens to the conjugacy problem when you take central extensions. And the reason it's sort of non-trivial is it involves calculating centralizers in these groups. And the centralizers in all of these groups can get very complicated, okay? And it's not just a matter of calculating centralizers, but when you take central extensions, you want to control how the co-cycle behaves over centralizers. And that's the key geometry. But I'm out of time, so I'll stop.
One quick question, and then there's coffee, and you can have much smarter than coffee. Francesco's fastest.
So the definition you gave of conjugator length makes sense for finally generated groups. Do you understand the spectrum there, or maybe for recursively presented groups?
No. But I haven't really tried. You can do so much with finite generated groups. It feels like cheating. Right? It's probably easy. Actually, it's probably easy. First of all, it's probably easy. You can probably come up with uncountably many exponents pretty quickly, I would think. No, but I haven't tried.
Okay, let's thank Martin again. And then